We are talking about graphing radical functions and transformations of radical functions. Graphing a radical function contains a radical expression with the independent variable in the radicand. So basically what that means is just that the x value is underneath the radical. And in this case, we're going to look at two different types. We're going to look at cube root and we're going to look at square root. So if we look at the square root, right over here, it says that the domain is restricted for x has to be greater than or equal to 0. And the reason that is because we can't have a negative value under the radical when there's an even value on the radical, because that will give us an imaginary number. And we only want to graph real roots. The range is restricted for y is greater than or equal to 0 because we're only concerned with the principal values of the square root or the positive values. So the x value in this case goes under the radical. So we take the square root of 1. We know the square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. And the square root of 0 is 0. So then we can graph and get a good graph of what the square root function looks like. We can also do transformations, and we'll talk about that in a little bit, but they're pretty similar to the way that we translate a parabola in vertex form. Then we have the cube root function. In here, it's the same thing. When we're graphing it, we want to find numbers that are exactly that we can calculate for the cube root. For example, we know the cube root of 1 is 1, the cube root of 0 is 0, and the cube root of -1 is -1. The next one that we know that is pretty easy to do is we can do the cube root of 8 is 2. So we go over 8 up 2. Or we can do the cube root of -8, which is -2. Whenever we have an odd radical up there above the radical, that means that our domain is not and our range are not restricted, because we can take the cube root of a negative value and that will get us an answer. That is a real number. Also, we can do transformations of the parent function the same way that we will for the radical. So the h is going to shift the graph along the x and y axis left and right. If we substitute a value that is where h is less than 0, that shifts the graph to the left. So if we substitute in a value, let's say it's -1, when we substitute in -1 into this function right here, x minus a -1 really becomes +1. So that's why it looks backwards. We substituted in a negative, but really when we look at it in the graph, it'll be positive, and we'll see some more examples of that later. If h is greater than 0, the graph shifts to the right. And then there's the note. H looks backwards because the negative sign in front of the h in the original equation. The k value is straightforward. It's going to move the graph up and down. If it's positive, the graph shifts up. If it's negative, the graph shifts down. The a value is the scale factor for the parabola and the vertical stretch or vertical shrink and reflection. So the a value cannot be 0. If I substitute in a 0 here, this whole thing becomes 0. A times the radical becomes 0, so then we just get y equals k. For vertical shrink, the absolute value of the a value has to be between 0 and 1. For vertical stretch, the absolute value of the a value needs to be greater than 1. And anytime that the a value is less than 0, there's a reflection over the x-axis. In that case, a is less than 0 means negative values. So here we have an example of what was graphed earlier, the parent function y equals the square root of x, and that's graphed for us here. And then we can look at what happens when we do the transformation. So we have a new transformation here. And the first thing is the parent function, when we're thinking of -1/2, if we substitute in -1/2, what that's going to do is It's going to flip it over the x-axis, and it will shrink it by a scale of 1/2. So let's do that. So that's the new function. Now if we put a negative out front, it gets flipped over the x-axis. And then if we scale it by 1/2, we're going to see that it's going to get closer to the x-axis. So this point up here, we have 1, 1, right? That's over 1, up 1. Then we did the scale factor of negative 1/2. What that does is it flips it over the x-axis, and it gets it a little bit, it gets it half as close to the x-axis. So over 1, down 1/2. And that pattern will continue. So if we go over 4, up 2, that's a point on the graph. We can see right there. What's half of 2? Half of 2 is 1. So we go over 4 and then down 1 in this case. Now we can look at what the transformation does. In this case, we have a -4, and we think negative, usually think go to the left, but this one is going to be backwards, because what we're actually substituting in the original equation has the minus sign, and we are substituting in a -4. So the -4 is going to move the graph to the left, as we can see there. And I'm sorry, that is a plus sign. So we're actually substituting in a +4 because the negative sign is there. So we substituted in a +4 into the equation, we can see there. So the graph gets shifted to the right 4, and then the -5 is going to move the graph down. So that is where that graph comes in right there, and we can see that. If we turn these two graphs off, we can look at the parent function of the cube root, and we can see that function still 0, 0, still 1, 1, still 1, 1, and one other thing we want to talk about with the square root. Both of these graphs go through the point 1, 1. Just a quick illustration. Okay, if we go over 8, up 2, that is another point on the graph. It's got to work to get it. Oh, that's too far. There we go. 8, 2, and -8, 2 is also on the graph. Or -8, -2 is also on the graph. Same thing. If we're looking at this function here, the first thing that we want to do is we want to look at what the scale does to it. We have the original function. We can see it's there. And what does the scale do? We're multiplying by 2, so actually that's going to make it twice as big. So if we're looking at this point, we go over 1, up 1. If the scale factor is going to double that, we're going to go over 1, up 2. So we should be up here at 1, 2. So let's see what happens. All right, and we can see that it gets stretched out twice as big. Same thing if we go to 8, 2. When it's stretched that big, it's going to go up to 8, 4. So we have that all set. Now we want to think about what happens when we add in these other parts, other transformations. So now we're looking at the translation here, and we're going to say +3. The original equation says x minus h. So what are we substituting in for h? In order for this sign to be a positive, we're actually substituting in a -3. Okay, that's why it's shifting to the left, because we actually substitute in a -3. Negative minus a negative does make it become a positive. And then the k value, straightforward, that's going to move the graph up 4. So we take our inflection point here, and we move it to the left 3, 1, 2, 3, and then we move it up 4, 1, 2, 3, 4. And then we have our inflection point, which has been moved. The original inflection point was 0, 0. We moved it to the left 3 for -3 and up 4 for our new inflection point. All of the other points get moved that way as well.